Well, that's better than farts. All right. Shh. Okay. Look at me. Let's get going. So today we're going to talk about a new class of reactions, oxidation reactions. Now, as the name would suggest, what do you think is happening when you are doing an oxidation reaction?
Oxidizing.
Oxidizing, which means what?
Adding oxygen.
Yeah, you adding oxygen, but it's actually a very specific piece of language, and it didn't start out that way, but sort of as we broadened our category, organic oxidation reactions are those in which a carbon atom is induced to make more bonds with oxygen. So yeah, it's all about bonding with oxygen, but it doesn't necessarily mean adding oxygen. It might mean that. It may mean adding oxygen, but it may also mean, well, let's see. Sorry?
You're gonna ask me what a tertiary alcohol is because I studied this today and I'm so mad that we didn't do that test.
Sorry?
I'm not. I'm really not.
I spent my whole art period studying alcohol.
You'll be okay. You'll be okay. I'm gonna do my attendance. It occurs to me because we'll do that. No, we'll start with the quiz tomorrow. This is just a longish note, so I don't want to.
The quiz on what? The journey race.
Yeah. Okay. So, I want you to draw for me.
Who's corresponding? Is that like your Google?
It's serious.
Yeah. Okay. I would like you to draw for me a tertiary alcohol. Okay, take a minute and draw for me the simplest tertiary alcohol you can, and leave space because we're going to have to do a reaction. So keep it simple. Also, while I'm here, going to print my cheat sheet because then I will avoid making a mistake.
Pretty sure that's the simplest.
Sure. Is that tertiary?
Oh.
Is it though? That's what I'm asking.
Check your notes.
I don't want.
Check your notes. Okay, glad we had this talk.
Do you want us to name it as well?
No, but you're on the right track.
This one now?
No, but you're on the right track.
Wait, yeah, I know where I went wrong.
Orlando, this one?
Sorry? Beautiful. Yeah, perfect.
Can I
Very
name
good. You can name it.
Yes.
Mr. Orlando,
Yeah.
can something make a quadruple bond?
Can something make a quadruple bond? No such thing.
That's supposed to be 1, 2,
But
3.
there is.
Just focus it.
No.
All right, get to it.
A carbon can quadruple bond to an iron, and the iron makes a
Iron
like
makes
Yeah,
three
yeah.
bonds to or
Yeah, okay. All right.
carboxyls.
Let's focus on the task at hand, shall we?
It's the chemistry.
All right, my attendance is in. Good.
Oh.
Yeah. Yes, it's perfect. Good job. All right, very good. Yeah, that was good. Okay, so I'm starting, and this is the first time I've ever taught this way, and I'm not sure if I'm going to regret it or not, but I'm starting with the example of a tertiary alcohol, and usually I actually start with the example of a primary alcohol, but instead, we'll go this. So when I said draw a tertiary alcohol, what did we draw?
2-methyl propane 2-ol.
Perfect. That is the simplest possible tertiary alcohol. There's all kinds of tertiary alcohols, but that's the simplest possible one because, of course, what is a tertiary alcohol?
It is an alcohol that is bonded in the middle on the same chain as a offshoot.
Yeah, it's an alcohol where the alcohol appears on the same carbon as a methyl chain. Or I shouldn't say a methyl chain, an alkyl
And it's in the
chain.
middle.
Could be any. Yep.
Would you even have to say two it's on the second carbon because it's the only carbon.
In fact, you would just call it methyl propanol,
Yeah.
propanol, not al. Okay. Now I want you, since we have chosen propane as kind of our base, let's quickly draw a secondary alcohol of propane, and in example 3, draw a primary alcohol of propane. I thought we might do well to draw all 3 first and then talk about what does or doesn't happen. So here we've got a tertiary alcohol. Here you're going to draw a propane, but it's going to be a secondary alcohol. And here you're going to draw a propane, but it's going to be a primary alcohol. And tell me now, what would the difference between these be?
Middle.
The secondary alcohol has no offshoot, and the primary alcohol is on the first carbon.
Okay, I understood what you said about this one. So in this one, the alcohol is on the first carbon, and of course you could draw it on either end. That makes no difference. I didn't quite get what you said about the secondary. Not to say you're wrong, just that I didn't get it.
The secondary one, you want the alcohol to be in the middle of the chain.
Oh, okay, on carbon
There's
2.
no offshoot. There's no methyl.
Oh, there's no alkyl branch there. Correct, yeah. So we have the hydroxide on carbon 2, but carbon 2 only has a hydroxide on it. There's no methyl group or any other alkyl group. Very good. Okay. So that is a primary, a secondary, or a tertiary alcohol. Now, the reason I mention this is that we think of an oxidation reaction being a reaction where you come in and add alcohol. Does that make sense?
Oxygen.
Thank you. Sorry. We think of an oxidation reaction being one where we would come in and we'd say, okay, we're going to put an
Oxygen?
Twice now, an oxygen on the chain. But in fact, sticking with that very specific definition, it just means that we're making more bonds to oxygen. We're going to have the carbon make more bonds to oxygen where oxygen is already. Does that make sense?
Theoretically, we can make the middle carbon.
Is this where oxygen makes more than 2 bonds?
No. In fact, what it means is that here, that can't happen. So here, if I take this tertiary alcohol and I try to oxidize it, and when we want to oxidize something, we put it in the presence of an oxidizing agent. These are things that induce oxidation reactions. There's a lot of different oxidizing agents. Nitrates tend to be good oxidizers, lots of different things. But what we go with very often are 2 very strong oxidizers, one of which is potassium permanganate, KMNO4, another which is potassium dichromate, K2CR2O7. Sorry?
Potassium dichromate is potassium and then dichromate. How do you know there's oxygen?
Well, the interesting thing is, it's not this oxygen that's going to get on there. In fact, they don't react with these. They just serve as catalysts. Because what they're going to do is all the oxygen on here is going to help induce this reaction. And we'll show you why.
So why isn't that?
So if we put KMNO4, well, because you know what you should know what the mangate ion is, MnO3. And from that, if you remember grade 11 chemistry, you should know that the permanganate ion is MnO4. So potassium permanganate is KMNO4. That's just standard ionic naming convention. Permanganate. So that's an ionic compound. So this is, remember, a catalyst. Specifically, it's not just any catalyst, it's an oxidizing agent.
What makes something an oxidizing agent?
It encourages oxidation to happen, and we'll talk about why that is. I know that's a bad answer, but trust me. So the first thing is, if you put a tertiary, that very is a Ryan answer. If you put an oxidizing agent with a tertiary alcohol, you get no reaction. And the reason I'm leading with the one that doesn't happen is I'm hoping we can look at that definition and see why not only does this not get oxidized, but in fact it's not possible to oxidize a tertiary alcohol. Bingo. Because if the idea is to make more bonds, if I wanted to make more bonds to this oxygen, carbon would have to make
It would have to just drop its alkyl chain altogether.
which it's not going to do, because those carbon-carbon bonds are very stable. So without breaking the chain, this can't make a double bond to that oxygen. So you can't oxidize a tertiary alcohol. And we're going to make a note of that. You can't oxidize a tertiary alcohol. And again, I know it's a little strange to lead with the non-example, but we lead with the non-example because, well, I don't know why. I just thought I'd try it this time and see if I like it.
It makes a lot of sense. You start with something where nothing happens, so everyone's like not expecting.
Yeah, that's what I like. I like my teaching to be a real mystery box of surprises. Ooh. But here, if we put this in the presence of an oxidizing agent, and what's an example of an oxidizing agent? Yeah, potassium permanganate. Oh, you get mad when I do my rounded capital M's. Is that better?
Yep.
Good.
I couldn't say anything in like biology or like chemistry when you like record the lessons. Rounded M's, and that's one of the scream rounded M's.
I'm sorry.
No, you won't.
I don't understand why you'd round an M because it's not supposed to be round.
Because I'm used to writing cursive M's, which are round. Then you might say, well, why not round your N's? Because cursive N's are round, and I don't have a good answer to that question. But anyway, my handwriting is always kind of half cursive. So I'm just going to remind us, not that you ever have to do this, but this is our oxidizing agent.
Cursive? You have a cursive class?
I would love to teach you cursive, but I'd like... You could, and I'm also going to show you that sometimes you'll just see that as the way we denote an oxidizing agent, or even sometimes that. But I like to write the actual thing. So potassium permanganate is a good oxidizing agent. Now here, we'll see why we need something with lots of oxygen on it to serve as an oxidizing agent. Because we know that by itself this is stable, right? You can have an alcohol. Alcohols exist. Not that any of you would know that, I'm sure. But alcohols exist. They're real things. But if this carbon is going to make more bonds to oxygen, then this carbon is going to make a double bond to
that alcohol.
But there's something preventing that. In fact, there's two somethings preventing that from happening. What are the two somethings?
So it doesn't need any more valence electrons.
Sure, and why does both the carbon and the oxygen have a full shell right now?
Because the oxygen is also bonded to the hydrogen, which makes it an alcohol.
Very good. And the carbon is also
has its
bound.
secondary hydrogen.
Good. So look here. This hydrogen and this hydrogen, these need to be induced to leave.
So they need something else to bond to.
If carbon is to form a second bond with oxygen.
You like go and buy a bunch of different colored highlighters and pens just to match the note.
I know. I'm sorry. So those two hydrogens need to be induced to leave if carbon is to form a second bond with oxygen. And as it happens, we don't have anything that these react with. Rather, we have something that when it floats by, it encourages these hydrogens to pull off. Basically, it encourages temporarily these hydrogens to just give up on the electron they're sharing here and just float away with a positive charge. Does that make sense?
That would be oxidizing agent.
And that is what the oxidizing agent does. Because the oxidizing agent, remember, this is an ionic compound. So when you dissolve an ionic compound, is this actually floating around as a KMNO4 single thing? No, it splits apart. What do we call that process? When you dissolve an ionic compound, it dissociates. So that means the potassium is doing nothing. The potassium is just floating around doing its thing. But this MnO4 is floating around with a negative charge, and not only a negative charge, but a negative charge with a whole boatload of oxygens there. Does that make sense? And basically, this MnO4 is able to float by and say, hey, you hydrogen, instead of hanging out with that oxygen in this polar covalent bond, what if you came and hung out with me in an ionic bond, right? And when they're close, it can do that. And then as they float away together, because HMNO4 is also just an ionic compound. As they float away, they will dissociate. And then the same thing can now happen to this hydrogen, which this hydrogen is attacked first, and now this hydrogen is already getting a bit of pull towards this oxygen. And then when the oxidizing agent floats away, it can pull it away with it too. Does that kind of make sense? That's the reaction mechanism here. But again, because it's an ionic compound, as it floats away, HMNO4 is just going to dissociate. So in the end, is the KMNO4 used up at all?
No.
No, it just temporarily comes in, induces a temporary reaction with these things, and then pulls them away. Yeah?
Wouldn't that be something similar to London dispersion process? Sort of?
Yeah, it's even more than that. I mean, really, it's using dipole force. Well, actually, it's using ionic forces. Really, it is the ionic charge of that MnO4 acting on those hydrogens that's pulling them away. So what we end up with is two, well, why draw two of them? Why not just say, we have an H plus ion here,
Oh, I hate this one.
and we have an H plus ion there. And then now we have this chain that still has that. It still has that, and that, and that, and that, and that. But now we have an oxygen here, which has an extra electron at the moment, and we have this extra electron on the carbon. And what can they do? They can form a double bond.
If these hydrogens are just hydrogen cations are just floating around, wouldn't that make it sort of an acid? Right?
Oh, yes, very good. If you were carrying this reaction out in aqueous solution, which is where you're going to carry it out, what is going to happen to your solution as you go? It's going to become acidic. And in fact, to keep the reaction going, you have to fight that acidity. You have to be constantly neutralizing that equation. So you would, well, KMNO4 isn't going to neutralize it because it's neither an acid nor a base. But you need, so very good observation though. This,
Alcohol.
not alcohol, you just need to use a base. Or you need to use a buffering system, which is something we'll learn about later in this course. But very good. This reaction makes the solution in which the reaction is happening acidic.
No kind of
Very
acid
good.
either.
Well, it doesn't matter. Acid is acid is acid. It's actually what you're making is permanganic acid, because what you're really doing, I suppose, is those permanganate ions are pulling hydrogens away and then dissociating again. So if you wanted to think of it that way, but really what it means is that in the presence of an oxidizing agent, a secondary alcohol will act as an acid in becoming, what is this?
Oh, that's
What is this? So now, yes, if we take propanol, propan 1-ol, and we oxidize it, we get two H plus ions.
What do you mean?
That's propan, oh, sorry, 2. Propan 2-ol. We get two H plus ions, and what would this be called?
propanal.
Not propanal. Close, but if it were propanal, where would that be?
No, propan 2-ol.
Very good. And we actually, this is the one ketone, actually this and butanone, that you don't have to name the carbon it's on, because there's only one carbon it could be on. I would love to. So, when we oxidize an alcohol, we get when we oxidize a secondary alcohol, we get a ketone. But listen, I don't want you to memorize that. Oxidizing a secondary alcohol produces a ketone and H plus ions. But again, don't memorize that. That would be such a silly thing to memorize, because it would be such a silly thing to memorize, because if you just look at it, what else could it do? Could this easily make an aldehyde?
Yeah.
Could it?
Well,
No.
we're primary.
If it were, but is it?
No.
No. So if you get a secondary alcohol, it's not going to make an aldehyde. The oxygen isn't going to jump onto another carbon. That doesn't make sense. So you don't need to memorize these rules. If you know that oxidizing means the number of bonds to oxygen is going to increase, well then, it is obvious where that's going to happen because there's only one oxygen on here. And it's also obvious what is going to have to leave for that to happen. Carbon can't make another bond unless it loses something. It's not going to break up the chain. Those are very stable bonds, carbon to carbon. So it's going to lose this hydrogen, which is what the oxidizing agent is doing. It's helping pull that hydrogen away. Oxygen is also going to have to lose its hydrogen, which is what that oxidizing agent is doing. It's pulling it away. And the result is that we get 2H plus ions, which you correctly identify as meaning that this reaction is an acidic reaction. It produces free H plus ions, and it releases a ketone. And we could even say, by releasing 2 H plus ions, it's acting as an acid. The pH of this solution will go down as this reaction progresses. Very good. Well, I think you are then equipped to do this reaction.
No.
Yeah.
Is it the same thing, but different?
Try it out.
You're missing a hydrogen. Yeah.
Sorry?
You're missing a hydrogen.
I am. I was going to draw it a different color, but forget it. You can draw it a different color if you want.
And is the catalyst the same, or does it matter?
Well, let's pick a different one. What catalyst do we want to use this time? Do we want to use potassium dichromate?
Potassium dichromate.
Yeah, that is potassium dichromate. It's a good one.
And then it functions the same.
Yeah.
That's just weird.
And there's a lot of oxidizing agents. If you go into our chemical supply room, you can see that we have a whole shelf. We always keep oxidizers away from everything else because we want to keep oxidizers away from things that can be oxidized easily. Good practice. And if you look on our shelf of oxidizers, it is almost all perchromates, manganates, and nitrates. Nitrates are very good oxidizers. Do you have some potassium permanganate? Potassium permanganate's fun.
Potassium permanganate is fun. Just 122.
Yeah, potassium permanganate is fun because it is this really fun colored crystal. Look at that.
What if you breathe it in?
Don't breathe in. Aren't they pretty?
You're telling me I can't smoke some?
Oh, nice color. I love that color.
Just to see if we just...
I think it's a really, that's cool. Yeah, I think it's a really beautiful color.
Right.
Looks great.
You like how I did the shape?
You did, because what's the hybridization state of that terminal carbon?
20 degrees.
Because it is. Oh, you're good. Time you could be great. But you can even see on here, it tells me that this is a oxidizer storage code yellow. So we know that when we buy this, you have to be very careful with it, because if you put this near alcohols or something, it will encourage reactions. If you put this near, anything that has especially big carbohydrates, right? Like if you put this near sugars or something, you're now taking a fuel source, something that has lots of big, long polymerized bonds, and putting it near something that can quickly provide oxygen. It's a real fire risk. But see what a great solution you get to it? Makes this really rich purple color. Yeah, isn't it lovely?
It's
That's the
stained
color
it.
of my room.
Yeah, it's a heavy stainer. You gotta wear gloves.
Stain is the color of my room. Yeah,
yes, my
definitely
favorite
stains. I got
flavor.
the same color stains on me.
Tastes like steak.
Man,
My favorite
I got the
flavor,
same
steak
color
flavor.
stains on me.
But it does look delicious, doesn't it?
Oh, I know. I've got the same same color stain.
Sorry?
That happened.
It's such a shame that chemicals so often look delicious. Like every time I make copper sulfate, I'm always like, that looks really delicious.
I painted my
not.
room burgundy and I got
I have not. Okay, so talk to me. What am I going to get when I do this?
You're gonna get an aldehyde. Oh, sorry.
No, that's good. I like that. So what's an aldehyde?
It's an oxygen double bonded on a terminal carbon.
Very good.
And you get your 2 plus H plus ions.
Yes,
Very good.
I'm
What?
loving that shape.
And yeah, if we're being shape conscious, which we always should be in organic chemistry, because we now understand the shapes we get, and that carbon still has a hydrogen left on it, right? Because in this case, we can randomly pick one of these two hydrogens. We know they're equally far away. These are what the oxidizing agent are going to act on.
But you can also pick the one off the bottom, right?
Yeah, it is. And again, that bond there can freely rotate, so there's no difference.
Yeah, it doesn't matter.
It makes no difference if you draw this oxygen up or this oxygen down, because the truth of that bond is it can rotate freely.
And it's another acid.
Now, this bond can't rotate freely, but that's okay because there's no chain going past it because oxygen only makes 2 bonds. Good. So we can, of course, draw that out again. What was the name of this? This was propan.
Al.
No, this.
Propanol.
This is propan 1-ol, and you do need to name the one on the alcohol. And it reacts to form propanal. Very good.
Plus 2 H plus ions.
Very good. We have an H plus ion.
Matter plus ions or cations. Do you care?
No, I'm pretty... So if you actually look at the... You could even call that just protons. You could say those are hydronium ions. Lots of things we can call them. But do you notice that if you start to understand, and this is what I wish, even when I was in second year organic chemistry, I didn't get it through my thick skull what was actually happening here. But if you look at it, it's really obvious what's happening, which is to facilitate this carbon making another bond to that oxygen, these 2 hydrogens have to go. So all an oxidizing agent is a compound that can induce these hydrogens to leave so that this bond can naturally form. That makes sense, right? Now, we'll make the note, even though we don't need the note because it's obvious, but primary alcohols oxidize to form. What is this thing called again?
Aldehyde.
Very good. Aldehydes.
I keep calling them adrenal ions.
And 2 hydronium ions. And I'm just using that term because you might not come across it very often. More often we just say H plus ions or whatever. But another accepted term for that is to say they are hydronium ions. Now, this is an oxidation that can occur, but then there's something really fun here, because take a good look at this compound. Let's take a look at this aldehyde.
We can oxidize it further.
Ah, yeah, let's take a look. Very good, Jonesy.
It just says so right there.
Whatever, you still read it. Take the credit. Come on. What's the problem, man? Someone tries to give you credit and you run away from it?
Yeah.
No, that was a screen. That was not a yawn.
My wife is one of these people who, when she yawns, it sounds performatively loud. And I'm like, just stop. And she's like, that's just how I yawn. I'm like, I don't believe you.
Ooh, we should get together one of these days and like write a script for a play next year.
I agree.
I am coming back.
Are you coming back?
Yep.
Good. I like it. Let's do it.
Because I'm looking.
I wanted to do one this year, but this year I'm just so dead. By the way, what's this bond angle?
120.
120. Because what's the hybridization state of that carbon?
SCH4U.
If we were to draw an energy level diagram, it would have a full 1s orbital. What would its second shell look like?
Forward.
Nope. It's hybridized.
Okay, so what do I have?
Got an sp2 and then 1p.
Okay, and how many sp2 orbitals are there?
3.
Yeah, and how many p orbitals?
1.
Great, what's this look like?
That's got...
Any lone pairs?
No, so they've all got to be filled. But you got to do one at a time. One in each.
So does it look like that?
No.
No.
You have to
No,
do-
those are lone pairs.
You have to
Okay.
do 2p first after again.
Yeah.
Well, I don't actually, but we have to think. Is there any lone pairs in that sp2?
No.
No.
So we'll leave it alone. That's good. That's going to be a sigma bond. That's going to be a sigma bond. That's going to be a sigma bond.
The 2p is gonna have one
Because that's going to be our...
double bond.
Yeah, that's going to be your pi bond. Very good. All right, you don't actually have to do that, but I just thought it'd be good to remember that once in a while.
It's gonna be on my test, isn't it?
I probably will throw a little throwback stuff on the test because it's good to keep it fresh in your brain. Because if you don't do it again until exam time, we forget about it, right?
You haven't even made the test yet, have you?
Think you do quizzes on it and not put it on a unit test?
Probably not.
I'm studying for a different subject.
You'll be all right. You're tough.
Yes or no?
Think for my.
You're also tough. Okay. So here, could we further oxidize this? Well, yes and no. Can I make another bond to this oxygen?
No.
No. But as it happens,
You can add.
once there is a double bond to oxygen here, this carbon is now primed to lose this hydrogen because oxygen is more electronegative. So we know that oxygen is, by virtue of its electronegativity, giving us dipoles in this direction, right? So we know that it is pulling electrons away from this carbon. But the thing about an electronegative bond is it actually has impacts elsewhere, because now that there's this really electronegative bond here, it puts a little bit of pressure on this bond because this carbon's hard up for electrons now. Does that make sense?
Yeah, so then
And so it has a little bit more of a pull on this, which means that it is relatively easy now to kick that hydrogen off. In fact, we saw that same effect here. The dipole here made it a little bit mini dipole here, which makes it a little easier to kick that hydrogen off, which is why this hydrogen will get kicked off and not one of these ones. Does that make sense? Well, we see that effect again. It would not be difficult to use an oxidizing agent to knock this hydrogen off. Now, if there's, well, that's where we're going to go. If there's nothing else around, when the oxidizing agent floats away, that hydrogen's just going to make its way and float back on. Does that make sense? But what if there was something else to put there? Because what do we have a lot of if we're doing this reaction where we normally do reactions? And where do we normally do reactions?
Over there, where there's like a million taps.
Sure. So for this, as long as you do this reaction in water, if when an oxidizing agent comes around and pulls this hydrogen away, if there happens to be a water there, well,
gonna make a move.
we can capitalize on that because there's also little dipoles here. So our oxidizing agent could act in two places. Give me an oxidizing agent I could use again.
A2CR2.
oh
Yeah, potassium dichromate works. You were probably going to go with potassium permanganate.
yeah,
That's fine. What's the formula for that?
permanganate.
Yeah.
MnO4.
Yeah, so we could have used KMNO4. That's fine. Either would work. I'm going to stick with this because it's what I wrote. But if you wrote the other, that's cool.
Is permanganate a radical? Right?
Permanganate is a radical.
Yeah,
Yeah,
okay.
it's
So
it's
that's
the
why-
manganate ion, MnO3,
That's
but
why
with
it's
one more
stealing.
oxygen.
That's why it has an electric charge. Okay.
Very good. Yeah, exactly right.
Can I-
So now our oxidizing agent in this case can work on this hydrogen and this hydrogen here. And you already know how this works then, because if that happens, those two hydrogens are going to find themselves floating around alone. They're not actually going to stay with the Cr2O7 in the long run. They're just going to be used by it they're just going to use it to pull away.
Doesn't this become
An alcohol.
no? Doesn't this become an acid?
Ah, let's take a look.
What was the name for it again?
You got to know that.
Carboxyl.
Very good.
Carboxylic.
Carboxylic acid.
Carboxylic.
So now if you look here, I'm going to redraw this O and this H as red just so we're really clear where everything came from. You certainly don't have to do that. But now carbon has a free bond. This oxygen has a free bond. What are they going to do?
They're gonna attack each other.
They're going to attach to each other. So this is a further oxidation. So aldehydes, I did the others in red, didn't I? I should be consistent.
Is it common for this to happen?
Yep.
When you put it in water? Okay.
Well, as long as you have what present?
Water. Or a catalyst.
Specifically, what kind of catalyst?
An oxidizer.
Very good. Catalyze, oxidize, aldehydes oxidize to form carboxylic acids. And can somebody remind me? Can somebody remember me how we say that?
Carboxylic acid.
Yeah, how would we name this carboxylic acid? This is obviously propane. What's this called again? Propane?
Propanal.
Al, not one, because if it were an one, where would that double bond to O be? Inside the chain, but it's an aldehyde, which means that the double bond to O, very good, is on the terminus. Plus water
Oh, I knew that.
yields with an oxidizing agent.
Tonic. No.
You're close.
Propan.
Propan,
Silic.
not silic. Come on, somebody tell me what's the naming convention for carboxylic acids? Very good. Propanoic acid. If you remember, we add oic acid.
Propanol. Oh, this is when I kept making pentatonic mistakes.
That's right, yeah. So propanoic acid. So we're going to use carboxylic acids a lot in this course. Now you can imagine then if you are oxidizing a primary alcohol, it could actually be a bit of work to figure out how to make it stop here and not progress and carry forward. Did that help you? Great. So a tertiary alcohol won't oxidize at all. A secondary alcohol will oxidize, but once it's oxidized, it's stable, right? That ketone can't be further oxidized. But if you oxidize a primary alcohol, you get an aldehyde, and an aldehyde itself can actually be oxidized. Well, if I wanted to oxidize a primary alcohol, but if I wanted to be sure that I didn't end up with an carboxylic acid, what would I want to make sure I wasn't using as my solvent for this? Water. Does that make sense? If I used water as my solvent, I'm going to encourage it to oxidize further. This is why sometimes in organic reactions we can't use water as a solvent. We have to use other things.
You switch the bracket on that O, called the arrow.
Where?
2 different types of brackets on the O.
Mr. Orlando, are we doing the back page as like homework? Or are we doing it
We'll do a couple together and then I'll send it to you as homework. Is that cool? Yeah, there's lots to do. So I want to give you some practice. Practice is good for you. Note that there's precisely one in here that I'm telling you is impossible, and it's not really sneaky because we know what's going to be impossible. What's impossible?
tertiary?
Yeah, you know you can't oxidize a tertiary alcohol. So I said sneaky, but really. Oh, guys, sorry. Oh, I switched my order here. Look here. I'm going to tell you which ones I want you to do.
Okay.
Because, sorry, I switched the order in which I was going to teach these lessons.
It's okay if I just make the compounds and
Methyl
wait for the
ether?
ones that I started doing number 2.
Diethyl ether. We'll come back to that. Don't worry.
Sorry, I didn't read it right.
No, you're good.
I'm just gonna make the compounds I know how to make.
You should see
So
the
we're
title.
gonna ignore page 1. Oh, I'm sorry about that.
So we're ignoring page 1.
Yeah. But
Finish making my 2 methyl mono, please. You might stop me.
I want you to do 7, 8, and 9 for now. I am so sorry. You see, amateur hour. I made a last-minute decision last night to change the order in which I taught these reactions. And you know what I didn't change? The homework. Didn't change the homework. See? Amateur hour. So these 3 will give you some practice. But the key thing is, look here. Like, it makes sense, right? Do we see how it makes sense? In fact, I'm going to throw together a few more practice questions just to give you more practice, and I'll throw those on the OneNote with solutions.
I think I'll probably do 10.
But listen, the answer is the right amount of homework to do is to keep doing homework until it makes perfect sense, right? I know that's like a cliche thing to say, but it's the truth. Methanoate?
Oh, I get to make another butanol.
I told you not to do that one, right?
What, the question 6?
Yeah, don't do
Yeah, 7, 8, 9.
7, 8, 9 is the one per day, or
7, 8, 9 is what I want you to do for now. And I'll throw you more homework up there. We will finish all this page after tomorrow's lesson. God,
Butane is my favorite.
damn it.
I have butane. I have meat everywhere. But I didn't know what